Okay, now we're moving on to conservation of energy, really stating energy initial equals energy final. Now, earlier when we were solving problems, really just kind of dealing with mechanical energy, we had, 1/2 mv squared, that's the translational kinetic energy. We had, say, mg delta y. Maybe you also had a spring in the system, say 1/2 kx squared. And then you would kind of do the same thing on the right side, right? But we're now realizing that this kinetic energy right here is not like the only thing, right? I mean, that's only if it's translating. So we need to modify this now, right? So what we need to do is add in, essentially, another term, right? So we have, it could be also be rotating, and so we have 1/2 I omega squared and say mg delta y. And then we have all these terms on the right side too. So this is 4 different types of mechanical energies. And this leads me into a great example of the great race. Who will get down to the bottom first? If I was rolling a hoop, an empty can, a solid cylinder, a sphere, or a box, which one gets down to the bottom, right, first? Or which one has the fastest speed at the bottom? So in this example, we want to look at maybe calculating the speed of them when they reach the bottom. So what we'll do is maybe first to kind of walk you through this a little bit is to kind of think of this through our energy bar charts, our LOL diagrams. So let's just consider one object. Let's say we look at just the hoop, for example, right? And we were to consider a system that has the hoop and the earth in the system. And we're going to assume, by the way, that there's friction, right, which causes it to roll, but we don't we don't have any thermal energy that's being generated, right? So basically all we have is just mechanical energy. So if we look at this now, this LOL diagram, we've got, gravitational energy, and you have like 2 types of kinetic energy, KT, which is translational, and say KROT, which is rotational. And we'll look at that at the end. Now, of course, there could be a spring here, but obviously there's no spring in here, so I'm not going to include this in the bar charts. Okay, so what kind of energy do you think we have in the system at the beginning? And hopefully you realize that it's not moving, so it doesn't have any kinetic energy yet, but it is up at an elevated height, so it does have potential energy. All right, so I'm just going to draw a little bar here for the gravitational potential energy. And so we'll just, I'll make it 4 bars here. And we're going to have no kinetic energy here. And then when it gets down to the bottom, we've got some translational kinetic. I don't know which one is bigger. I'll just assume that maybe 3 bars are translational and 1 bar are rotational. I don't know exactly, but we just know that the sum of the blocks, right, at the beginning, the sum of the blocks at the end are equal to each other. So essentially, energy initial equals energy final. We have gravitational potential energy that's being converted into translational kinetic energy and rotational kinetic energy. So you have mg delta y equals 1/2 mv squared plus 1/2 I omega squared, right? And in order to see the speed at the bottom, we have to kind of do some changes in here, right? So one of the big things you may notice is that if we're looking for the speed at the bottom, we want to get rid of the angular velocity term, right? So if you recall, right, v equals r omega. So we can replace omega with v divided by r. Now, this is important to understand that we can only use this if it's rolling without slipping, right? So if it was slipping, then we couldn't be using this equation. We can't be using this equation. So we're going to put that in here, right? And we're going to have 1/2 mv squared plus 1/2, and then over here we're going to write in a v divided by r quantity squared. Now the other thing, and this is going to change depending on what you have, is the rotational inertia, right? So if the rotational inertia of the hoop, right, is what? So let's go back to our earlier in our notes. And the rotational inertia of a hoop, basically a thin cylindrical shell, is given by mr squared. So we're going to be using that equation now. So let's plug in an mr squared here. So we got, then over here we have mr squared. Now, beautifully, some cancellations will occur. You'll see in a second. Mg delta y, 1/2 mv squared on the right side, plus 1/2 mr squared, and then v squared over, well, this r, by the way, because it's on the outside of that hoop, is just capital R, really. So capital R squared, right? So remember that, like when you look at the hoop rotating around, at some angular velocity. And if we want to find the tangential speed of it, we just basically take the radius of it, right, multiplied by the angular velocity. All right. So if you wanted to find the say like in the middle somewhere, then you have to know that radius at that point. But since it's not slipping, we're going to be using the radius of the entire hoop. Now, some nice things cancel out in here. You may notice this R and this R, these R squared terms cancel out. And then you may also notice that the M here and the M here and the M here beautifully cancel out as well. So we end up with basically G delta Y equals 1/2 V squared plus 1/2 V squared. So that is going to give you V squared, right? Equals G delta Y. So V, in this case, is equal to the square root of G delta Y. And that's G for the hoop. Sorry, that's V, the velocity of the hoop at the bottom. All right, and I don't think we have any numbers in here. We're just kind of coming up with that expression. Oh, by the way, we're using delta Y, so let's replace that as G with a capital H. Now, this was all for the hoop, right? How would you change it if this was a, say, I don't know, a solid cylinder, right? So what changes in the problem? Maybe I will kind of show it to you. So basically, the one big change is this rotational inertia right there. That's the change that we're going to see. Let me highlight that guy, right? So what we need to find is what is the rotational inertia of, say, a solid cylinder, right? So you go basically through back to your notes, and a solid cylinder is 1/2 mr squared. So if we change hoop to a cylinder, we are basically repeating this whole solution. So where I saw mr squared, that's now going to be a 1/2 mr squared. So now we will not have half here. We will have a quarter there, right? And still the same things. And over here, this will be a quarter, right? And a quarter plus a half is 3/4. This becomes 3/4 here. And so for the cylinder, right, solving for V, we will get the square root of 4 GH all over 3, right? There's a 4/3 instead of just a 1 here. Now, hopefully you can see that the cylinder will basically have a faster speed than the hoop at the bottom. So who do you think wins then? So I hope that you realize that the speed of the cylinder is faster than the speed of the hoop, right? And that means that the time that takes the cylinder to go down is going to be shorter than the time it takes for the hoop. Now, how do you explain that besides just sort of talking about like looking at the equation and deriving it? My feeling is to take a look at this sort of energy bar chart. Perhaps at the beginning, they both have the same potential energy because they both all have the same mass and height and so forth. And they both lose all the potential energy, right? Get down to the bottom. But the hoop, let's say, puts a lot more of its energy into the rotational, and then therefore it has less like translational energy. So like, let's say there's like 3 bars here and 1. That would be, say, the hoop situation. But if you were to replace this with the cylinder, right? The cylinder would be a little bit different, right? This is a solid cylinder, so its rotational inertia is smaller, so it's easier to rotate. And so the cylinder will then therefore have, picked up more kinetic energy and have less rotational energy. It doesn't have to do as much work. So because I is smaller, its rotational energy will be smaller, and then therefore its kinetic energy will be bigger, and so have a faster speed, right? Remember, this is like 1/2 mv squared. So less of that total energy is going into rotational energy. It's easier to rotate, right? I smaller, and therefore it then is able to get a greater translational kinetic energy. Okay, enough of me talking. You can go through the rest of the problems and do a sphere, do a box. It's interesting when you do the box, by the way. The box will only have potential energy and only translational. It won't have any rotational energy because it can't rotate it. So hopefully you'll see that the box is the one that actually is the fastest of them all. because it converts entirely its potential energy into translational kinetic energy because it cannot rotate it, right? So it's the one that gets down to the bottom first. Okay, that's it for this example.